Okay, so first thing that I want to discuss is the idea of the hole in the ozone layer. We have a layer of ozone that is in the stratosphere, which is actually protecting us from harmful ultraviolet radiation. And what we know is that if we look at the DNA molecule, I'm just going to draw something for you. DNA is composed of 4 nitrogenous bases that are strung together in ever-changing sequences, and these sequences determine our genetic code. So we use the letters A, T, C, and G to abbreviate these chemical entities, which are adenine, thymine, guanine, and cytosine. And I'm going to show you something having to do with thymine. So DNA, if we look at a DNA strand that's about to replicate itself, and I'm just going to write some random combination of nucleotides. These are the base pairs here. So let's say we have a strand that starts out with a C, then it's a G, and then make this an A, and then a T, and an A. And it's copying, it's going to be base paired with its complementary nucleotide. So cytosine's complement is guanine, guanine's is cytosine. These would be the base pairs. Thymine is adenine, and adenine, of course, is thymine then. So this is this would actually make a strand of this. This would make a strand. Let's see if I can show you this. This, when it's replicated, will make a strand. These two strands will separate, and this will make a strand that will be identical to this side. And this strand will make a strand that's identical to that side. The problem is this, that when you have 2 thymines next to one another, which you have a lot of, and these things are irradiated with ultraviolet radiation, that's what we call ultraviolet C, UVC. This is, the ultraviolet spectrum is divided up basically into 3 regions. One is the long wave region that goes from almost up to the visible, maybe around 400 nanometers, down to about, I would say about perhaps about 320 nanometers. And then from about 320 or 315, we go down to 280, and that's called UVB, which is more energetic, to 280 nanometers. And then below 280 nanometers is the UVC region, and that can go down to 200 nanometers, even lower than that. That's the most energetic ultraviolet radiation. So ultraviolet radiation that's actually going to make it down to the ground and will actually interact with these base pairs. What it does is it actually causes these bonds here, breaks these bonds, and causes them to reform in this fashion. And this particular, this 4-membered ring here, 4 carbon atoms that are attached this way, it's called a cyclobutane ring. But this is what is known as a thymidine dimer. And these dimers, what they do is, when the DNA polymerase is trying to read the structure here, so it sees this, it puts a G here, it sees that, it puts a C here, it sees this, puts a T here, then it sees something very strange. It sees these 2 T's bound together, and it actually causes a chink in the, it causes a bend to occur in the DNA chain in such a way that it actually stops the polymerase in its tracks. The polymerase may terminate the sequence at that point, so that it stops adding additional base pairs to the chain. So you're going to get a truncated, duplicated DNA. It won't have the right number of base pairs in it, or it may actually add some random base pair and then continue copying, in which case you've got a genetic mutation. In either event, it's not something that you want to actually have happen. So it's a bad thing. So what actually happens here is that oxygen molecules can actually help us out, because oxygen absorbs, the oxygen molecule can actually absorb a lot of the very, very energetic energy here. So oxygen looks like this. And it also has a form that looks like this, which is also a contributor to this. It's what we call an oxygen diradical. And these two forms of oxygen will actually absorb ultraviolet energy down around the 200 nanometer region of the spectrum. Now ozone, which has 3 oxygens in it, this is another one of the allotropic forms of oxygen. This is diatomic oxygen. This is stuff that we breathe. The ozone looks like this. And it also has 2 what we call resonance forms. Ozone on average has, we say this has a bond order of 2. It's a double bond, but ozone's bond order is somewhere between 1 and 2. We can look at the actual bond length, and we'll find that the bond length here for oxygen is shorter than it is for ozone. That means that it's actually easier to break apart an ozone molecule than it is an oxygen molecule, and we need less energetic ultraviolet light to do so. So this is what the ozone would look like. And this would be the ozone molecule, and this is its resonance form here. But on average, it's not that there's a double bond and a single bond. It's on average, it's as if each one of these has a 1.5 bond character to it. So these are actually easier to break down. And this ozone will actually have an absorbance that's going to go somewhere from about 230 to about 280 nanometers. And so any ultraviolet radiation in that region of the spectrum is going to be picked up by the ozone. But there's a problem, because for years we've been putting into the atmosphere things that are called chlorofluorocarbons. And these things actually react with the ozone, this protective layer of ozone, and destroy it. So what we get is, I'm going to show you with a simple chlorofluorocarbon. This is called chlorotrifluoromethane. And if we irradiate this with H-nu, again, the H-nu means ultraviolet radiation. This is the energy is equal to Planck's constant H times nu, the frequency of the ultraviolet radiation. What we're seeing here is that if we irradiate that, we're going to form CF3 dot, that's a single electron, plus chlorine dot, that's a Cl here, sorry about that, Cl dot, single electron, and that will actually react with ozone. It's the chlorine atom. This chlorine radical, or chlorine atom, is going to react with ozone, and that will form oxygen plus chlorine oxide as a radical. So here we have that. And then the chlorine oxide can react with more oxygen, the monatomic oxygen, which actually forms from the ozone itself. When the ozone absorbs at, say, 250 nanometers, the ozone is broken back down into oxygen. Plus atomic oxygen. So there's atomic oxygen that's available from the ozone. That chlorine radical reacts with the chlorine monoxide radical reacts with the oxygen radical, and that forms chlorine radical plus oxygen. So the ClO plus O reacts to give you chlorine, and that's just giving you more chlorine to destroy more ozone. So it's a vicious cycle. That's what I wanted to show you. That's just a vicious cycle. We pretty much addressed this issue, though, by just taking these chlorofluorocarbons, which had been used for many, many years as refrigerants and also as propellants in these spray cans, and we kept putting them, spraying them, and the refrigerants would leak out of these closed systems, and these things would have ultimately get back up into the stratosphere. And now we've pretty much eliminated these things. So one would hope that over a period of time, we'll see the natural processes by which ozone actually forms start to close up these enormous holes that began to appear over the poles, the polar regions of the Earth. We're getting these huge voids of ozone. So the threat was that ultimately, if that continued, we would all be irradiated by so much ultraviolet radiation that we'd see, and we actually are seeing increases in things like skin cancer, etc., because of this. So this is something that hopefully over a period of time, this will actually dissipate somewhat.